there are really kind of two factors that go into looking at the overall molecule's polarity, which is really what we're trying to get to in this chapter, because ultimately if we want to be able to predict why some substances are liquid at room temperature, why others might be gases or solids, why a substance has a higher boiling point or a lower melting point, or why two substances are able to mix together and dissolve, like sugar and water, whereas other substances form separate layers like oil and water. The ability to answer those questions and maybe make predictions about properties for new substances come from looking at an individual molecule's polarity, looking at an individual molecule's dipole, whether it has opposite charges on opposite ends or not. And so to answer questions like that, we have to look at the shape of the molecule, and we have to look at the individual bond polarity, which is what the quiz question was about. And so there's a difference between having an individual bond that's polar versus having an entire molecule that's polar, and we'll see that as we go through today. But even before we can talk about that, we have to look at the geometry of a structure, because if we're trying to imagine this thing in 3 dimensions and where there might be areas of positive charge and negative charge, we have to have an idea of what its shape is, what it looks like 3-dimensionally. And that's what molecular geometry is all about. So to understand molecular geometry, we will invoke something called VSEPR theory, which is the valence shell electron pair repulsion theory. And it pretty much is exactly what the name of it says. So if we break that down, what we're talking about is the valence shell electrons. They're usually in pairs. So basically what we're talking about is the valence electrons, the pairs of electrons around an atom, whether they be lone pairs or bonded pairs. It's those pairs that repel one another. Right? We already know electrons are all negatively charged. We already know electrons repel one another. So this basically all we're saying is when I have multiple pairs of electrons around an atom, so say I have just some generic atom here, if it's got some electron pairs around it, it could have a lone pair, it could have a single bond, maybe a double bond. All we're saying is those electron pairs repel one another and they spread out. That will determine the shape of the structure. Right? And the reason for that is because we have to also keep in mind that the pairs of electrons around an atom are occupying a lot of space. They're in these orbitals, right? So this atom, whatever element X is here, it has an orbital holding that lone pair. And it has an orbital sharing electrons with another atom here, a couple orbitals sharing electrons with a couple pairs of with an atom here on the other side. And those orbitals take up some space. If you outlined, where the majority of the electron density would be in those orbitals, so this one here is a molecular orbital, because whatever atom X is sharing electrons with here, those electrons are spending time around both nuclei. And I could say the same thing here, so that electron density is going to be all over here. And if I were to look at that, I can see now there's an area right in here where those electron orbitals overlap. Right, this orbital here between X and Y, it's overlapping a little bit with X and Z. Right, and if I look at the shape of this orbital that the lone pair is in, that's also overlapping a little bit in some of these areas. So there are areas right next to the nucleus where one orbital, which is full of 2 electrons, and another orbital, which is full of 2 electrons, overlap a little bit. And we're kind of then putting like 4 electrons in the same area. That causes repulsion. That's what VSEPR theory is. Basically it says we want to avoid this as much as possible. We can't avoid it altogether, but we want to avoid it as much as possible. So what we don't want to do is to think about this structure's geometry being all crunched together. I don't want to compress that angle there between those things bonded to X to a smaller angle than it needs to be, because then when I think about the electron density around X and Y and the electron density around X and Z, and where that electron density is going to be located, well, now I have a lot more area of overlap between those orbitals, and in that area of overlap I get a lot more repulsion. it's just not naturally going to exist like this. Because if there's space to spread those out, they're not going to come together and overlap and create repulsion. I could use some energy and force them together and overcome some of that repulsion. But if I did and then I let go, they would just pop back out to the largest angle they can get. Right? So basically, when we're thinking about the shapes, we just have to figure out, first question is, how many electron groups are around the atom? Because the more electron groups, the more, the less space there is between them. The fewer electron groups, the more they can spread out, and that will result in a different geometry. We're going to focus on these ones because the other two are rare, because if I put 5 or 6 atoms, if I have a central atom, I put 5 or 6 atoms attached all to that one atom, it's going to go beyond the noble gas configuration, and we don't really see that very often, so we're not going to worry about those. So here are some examples. So I've got 3 molecules here, and the textbook uses these three to illustrate because they have differences in the number of electron pairs around them, or electron domains. So the reason the textbook uses electron domains rather than electron pairs is because a double bond counts as one domain. Right, so a double bond is kind of like these 2 electron pairs in the double bond are okay with one another. They're not repelling from one another. I need both pairs to be in between the carbon and the oxygen in the double bond. So they're not going to be spreading out from one another. So ultimately what I have here, when I have a double bond, is that's like one area of electron density. And when I have the double bond on the other side, that's another area of electron density. So I want these 2 areas of electron density to be as far apart from one another as possible. To avoid repulsion. Avoid overlapping of full orbitals. Overlapping of full orbitals is destabilizing and not likely to occur. So what I'm looking for is, on an atom that has more than one other atom attached to it, how many electron domains are there? An electron domain is either a lone pair, a single bond, a double bond, or a triple bond. Right, so when I have CO2, I've got a double bond on this side of the carbon, a double bond on that side. That's 2 electron domains. And so they want to spread out from one another. Of course, it's going to be linear, right? So I wouldn't draw the shape of CO2 like this. That's not how it exists. It doesn't exist like that because a 90-degree angle would cause these electron domains to be too close together, and repulsion would push them out. They wouldn't stay at that angle. Okay, so when I've got 2 domains, it's going to be linear. Another option is 3 domains. So here's an example of that. I've got a double bond on one side of the oxygen, a lone pair. So a double bond is a domain, a lone pair is a domain, a single bond is a domain. 3 domains. So those 3 domains need to spread out. Right, so if I have a central atom, I'm going to attach 3 things to it, leaving as much space between those 3 things as possible. What's the greatest angle I can create that leaves the most space for those 3 things? Yeah, it would be like a triangle. It would be 120 degrees, right? So if I have the oxygen here in the center of the O3 molecule, right, there's 360 degrees around that. And so if I'm working in a plane and I have 3 things, I take 360 divided by 3, and I find that those 3 things, one was a lone pair, one was a double bond, and one was a single bond. Those 3 things should all be at an angle of 120 degrees. That spreads them out from one another as much as possible and avoids the repulsion as much as possible. So you might say, well, why are you limiting yourself to a flat 360 degree circle when you have 3 dimensions? You have space all around that central oxygen to put those electrons. Well, you can think about that as well. You can say, well, what if I took this oxygen-oxygen bond and try to lift it off the paper? Is it going to be farther away from the other 2, or is it going to start getting closer? It only is going to get closer. And so the angle here is 120. If I try to pull the oxygen up off the page, I'm approaching a 90-degree angle if I pull it straight out of the paper. So it's going from 120 to smaller and smaller angles. That's only creating more and more repulsion. So what turns out, geometrically, when I have 3 electron domains, the best way to spread them out is actually a 2-dimensional flat structure, or a planar structure. So that's what we end up with when we have 3 domains. When we have 4 domains, now we have even more repulsion, because now I have an electron pair there, a lone pair. That's a domain. That's taking up space. I've got this orbital here. That's taking up space. This orbital here full of electrons, repelling the other orbitals that are full of electrons. So now I've got 4 things. I've got 4 electron domains, and I still want to spread them out as much as possible. So in this case, if I imagine the molecule on a flat piece of paper, what would the angles be? They'd be 90 degrees, right? The best way I can spread out 4 items is 90 degrees. I take a 360-degree circle, divide by 4, I get 90. 90-degree angles creates a lot of overlap between those orbitals, though. And since I do have 3 dimensions, I can create larger angles and avoid some of the repulsion if I push some of these groups in and out of the plane of the paper to avoid some of that repulsion. So let's look at what some of these shapes look like. Hard to see on a 2-dimensional piece of paper. So the textbook uses balloons to show that when you put 2 balloons together, the edge of one balloon will kind of bump into the other, and that will cause them to spread out. So 2 electron domains is linear. So the balloons is also nice because it's approximating the shape of these orbitals. So an approximate shape of what the orbital shape is 3-dimensionally when you have a lone pair on an atom, or when you have an orbital that might be overlapping with another atom at the end of that. And so it's also, fairly reasonable analogy to make. So when I have 3 balloons and I connect them all at the end, then I get a trigonal planar geometry. And when I have 4, I have what's called a tetrahedral. Right, so this one's a little tricky because it is 3-dimensional. When I have a tetrahedral, so we're not going to worry too much about 5 and 6, but when I have a tetrahedral, I can put 2 of the groups, so if this is my central atom, I could put 2 of the groups in the same plane as the paper. 2 and only 2. I can never have more than 2 groups in the same plane when I have a tetrahedral. If I have 4 total groups or 4 total electron domains and they're repelling and spreading out as much as possible, I can only put 2 in the same paper, and the angle here will end up being 109.5 degrees. The other 2 will be pointing away from these 2. One will be coming out at you a little bit, and the other one will be pointing away a little bit. It's hard to draw. It's hard to show that. So what you'll see a lot is something like this for the tetrahedral. Now to me that doesn't look great because it's 2 dimensions. It looks like the angle here is really small, right? But you've got to remember that one of these groups is coming out at you, not straight out at 90 degrees, but out a little bit at an angle, 109 degrees, 109.5, and the other one's pointing away. So there's actually the same angle, the same distance between these 2 as there is between these 2 and these 2 and these 2 all the way around. All the angles are 109.5 degrees. So this is just another representation of the same structure. So I want to make sure we understand the terminology as well. So when I ask you a question on the exam, you know what I'm asking for. I might ask you about the electron-domain geometry. And that's what we've been focusing on so far, right? So that is where, and that's really what you need to look at first. Even if ultimately I'm asking about the molecular geometry, you need to analyze the electron-domain geometry first. And so that's what we said so far. We said if you've got, let's just go back here. If you've got an atom and it has some lone pairs and some bonds, let's say it's got 2 lone pairs and 2 bonds. If I want to know what the bond angle is, or if I want to know what the geometry is for the molecule, I still need to look at the electron domain geometry first. So the idea there is I recognize that the lone pairs or in orbitals that are taking up space, and they're going to be repelling one another, and they're going to be repelling the bonded pairs. And so, because I've got 4 electron domains repelling, the electron domain geometry for this molecule is tetrahedral. That shape we just saw. It's not going to be linear. I could imagine that my element X might be bonded to things and that the angle here would be 180, and you might say, well, that's a larger angle, so that should seem better because it should avoid repulsion. But if I create a 180-degree angle and make that linear, where am I going to put my lone pairs? I would have to put them at like 90 degrees, which is not as favorable as 109. So the idea here is I want to look at the electron domain geometry first, because that will allow me to see what the angles are. Then I can look at the molecular geometry, which is usually ultimately what we're using to describe the shape of the molecule. And I can say, well, the molecular geometry is really just where the atoms are located and what type of shape that creates. So if the atoms are located in a straight line, the molecular geometry would be linear. If they're located here at an angle, then the molecular geometry would be bent or angular. There's a difference. There's a huge difference. If I had water, a water molecule that was bent, its properties would be totally different from a water molecule that was linear. If water was linear, it would not be a liquid at room temperature. If water was linear, it would not be able to dissolve a lot of polar substances like sugars and salts. Its properties would be totally different. The reason water behaves the way it does is because of its bent geometry. And so if I have a structure and I want to determine what the geometry is because I want to later predict what the properties of that substance might be like, I need to determine its geometry first. I need to recognize first what the electron group geometry is. In the case of water, it's an electron group geometry is tetrahedral because it has 2 lone pairs and 2 bonds. That's 4 electron domains. So when I count the number of electron domains, that tells me the electron group geometry. 4 is tetrahedral. Then, when I'm just looking at the molecular geometry, I say, okay, well, I know that the lone pairs are here, and they're creating repulsion. They're creating the angle of about 109.5. But when I'm looking at molecular geometry, I'm just looking at where the atoms are and looking at the shape that that's created. Once I know where the atoms are placed in space from the electron domain geometry, then I ignore the electrons after that and recognize, okay, if the atoms are placed in space in some geometry, I just label the name for that geometry. So what would the name for the molecular geometry be if I had an atom that had 4 other atoms attached to it and no lone pairs? Well, that would be tetrahedral. So maybe write this down. When a central atom, all of the central atom's electron domains are bonds and no lone pairs, then the molecular geometry will be the same as the electron domain geometry. So, say it again. When an atom has all of its electron domains as bonds and does not have any lone pairs, then its molecular geometry will be the same as its electron domain geometry. And then conversely, if it does have lone pairs, it won't be the same. And so, in the case of the water, the electron domain geometry is tetrahedral, but the molecular geometry is bent. But I have to get the electron domain geometry first, because if I don't, and I just forget about the lone pairs altogether and just look at the atoms, I would probably predict that water would be linear, but it's not. Because of having 4 electron groups, those 4 electron groups have to be arranged in a tetrahedral geometry, which means if only 2 of them are connected to atoms, then I end up with a bent or angular molecular geometry. So, yeah.
Just to reread what you said, tetrahedral, one of the central atoms has an electron domains, then electron configuration.
Say that again?
I must have heard you wrong. What did the sentence say? Tetrahedral, when a central atom has an electron domains, and it's an electron configuration.
So what I said was, when you have an atom, if you have an atom,
Yes.
and all of its electron domains are bonded pairs, and there's no lone pairs, then the label you give for its molecular geometry will be the same as its label for its electron domain geometry. So if I have 5 atoms bonded to my central atom, don't worry about it. I won't ask you about that. All right, so let's look at a couple more examples. So here I've got the ozone that we were talking about. So we said about ozone, how many electron domains are there? 3. There's a lone pair, a double bond, and a single bond. Remember, a double bond or a triple bond only counts as 1 electron domain. So for the oxygen in the center, it's got 3 electron domains. And when I've got 3 electron domains, the electron domain geometry is trigonal planar. Trigonal means 3. You've got 3 electron domains. Does that make sense? Whatever it means, it's flat. It's all in one plane. Nothing is coming out of the plane of the paper or going back behind. And that's what we have, right? We said when I have 3 electron domains, the space that those occupy as they repel one another, they're going to be spread out at about 120 degree angles. And that will be in the plane. That's the geometry I get when I have 3 groups repelling around the central atom. So again, that's with a trigonal planar electron domain geometry. But, in this case, since not all of my electron domains were bonds, one happened to be a lone pair, the molecular geometry is not the same as the electron domain geometry. And if I'm just looking at the molecular geometry, once I realize that the lone pair is there, it's repelling, it's causing these to come down at an angle instead of to be linear, then I just look at where the atoms are as a result of that taking place, and I realize that there's an angle there, and I can predict the angle should be about 120 degrees. Questions about the geometry of that? What? Yeah, that's why I'm saying if all of your electron domains were bonds and none of the electron domains were lone pairs, then the labels would be exactly the same. Be the same label. So the only difference is if I do have a lone pair, I have to realize it's there because it's repelling, it's creating the angle between the other bonds. But usually later when we analyze like polarity and stuff like that, we don't have to worry about those lone pairs. They're there. We have to worry about them now because they will determine the shape that we get from the molecule. But once we have that shape, once we realize what the angles are, then we don't need to worry about the lone pairs anymore because at that point we can analyze the polarity and the properties of the substance once we have it, the shape of how the atoms are connected.
Okay, so when you say it's bent, you want to say it's bent at 100 degrees?
Probably won't ask you the angles on these, but it wouldn't hurt to know them. Bent would be adequate if I just asked you for the molecular geometry. All right, so here are the ones that you need to know. There's not that many of them. So if I've got 2 electron domains and no lone pairs, here's the molecular geometry. So let me add another column to this. I'll add a column here, and I'll call this electron domain geometry. So that's probably, we would want to analyze that first, right? So if I've got 2 electron domains, that's going to be linear. If I've got 3 electron domains, that's going to be trigonal planar. If I've got 4 electron domains, that's tetrahedral. Right, tetra is a prefix that means 4. So if I have 0 lone pairs, then the molecular geometry and the electron group geometry are the same. See that here, here, and here. If one of my electron domains is a lone pair, though, then when I'm looking at the actual molecular geometry, I see a difference between the electron group geometry and the molecular geometry. So there should be something like this, a chart that's similar to this, I think, on your formula sheet. Yeah, so this is it. This is labeled as shape, but it should be labeled as molecular geometry rather than shape. So just what I said was, if there's 0 lone pairs on the central atom, right? So let me also clarify. These shapes are labels for an individual atom. They're not labels for a molecule as a whole. And we'll see some examples to illustrate that a little bit later. But we're looking at an individual atom. What is the shape of that atom in terms of what shape is created when I look at the other atoms attached to that atom? So when I'm analyzing the geometry of an individual atom, as long as there's more than one other atom attached to it, there's a possibility that it could be one of these options. So I've got to first look at how many electron domains there are. Then I look at whether those electron domains are lone pairs or not. If all the electron domains are bonds and none of them are lone pairs, then the electron domain geometry will be the same as the molecular geometry. So hopefully this will be easier for you as we go through and look at some examples with some actual shapes. So they also outline kind of a step-by-step procedure for doing this. Just to point out, you have to be able to start with a reasonable Lewis structure. If your Lewis structure doesn't work, doesn't have complete double gas configurations, or if it creates a bunch of unnecessary formal charge, it's probably not going to be leading you toward a reasonable geometry. You have to start with a reasonable Lewis structure. Then look at each central atom in the structure. If the structure has only one central atom, and all the other atoms are attached to it, then you only need one to label one geometry for that one atom. If your Lewis structure has more than one central atom, something like this, I need to label the geometry for X, and I need to label the geometry for Y. They may or may not have the same geometry. I have to analyze them one at a time. So I would do each of these steps for X, and then I would separately do each of these steps for Y. So I would count the electron domains around X. There's 3. Double bond, single bond, single bond. That's 3. Determine the electron domain geometry for X. Trigonal planar. Look at where there are or aren't lone pairs around X. There are no lone pairs around X, so its molecular geometry is the same as its electron domain geometry, which would also be trigonal planar. Then I would do Y. Y also has 3 electron domains, a single bond, a double bond, and a lone pair. So its electron domain geometry is also trigonal planar. But it only has 2 atoms attached. This lone pair is important because it causes these 2 atoms to be attached at an angle of about 120. But when I'm looking at the molecular geometry, I'm just looking at where those atoms are. And since they are at an angle, that tells me that's bent. If you had drawn your Lewis structure like this, that's a little misleading. Drawing your Lewis structure like this is okay for a Lewis structure because it has complete noble gas configurations for X and Y. But it's a little misleading because it makes it look like Y as an individual atom is linear, and that the other atoms attached to it are attached at 180 degrees. That would be the case if the lone pair wasn't here to repel them. Right? So that's how important the lone pairs are. And that's why you have to really look at the electron domain geometry first, because that lone pair's presence will cause the bonds to not be linear in this situation. It will cause the bonds to occur at an angle. And as we said, the properties of that structure might be totally different depending on whether the bond has an angle or whether it's linear.